Hey guys, we're going to start our unit on logs. We're going to start by learning how to graph logs and then exponentials, which is the inverse of logs. So I'm going to do it on our yellow packet that we have. The first thing that we have is b to the x. This is an exponential. So in your notes, you're going to write exponential graph. Okay. And as we learned before, when we learned about our functions, the exponential graph always goes through 0, 1. Remember, we did the 0, 1 when we did our what the functions look like. Okay. So it always goes through 0, 1. And the reason why is because if I have a function that's y equals b to the x, it doesn't matter what b is if x is 0. Okay. If I have anything to the 0 power, we always get 1. So that's why the exponential graph will always go through 1. The only thing that will change that is if you add or subtract and you shift that whole graph up 1 or down 2 or whatever it is, okay? So it'll always go through 0, 1 unless you have a vertical shift or a horizontal shift, and then you're just going to move that point, which we kind of call our point of origin or our starting point, is going to be where that changes, okay? So when we talk about an exponential graph, you need to know that there's going to be a horizontal asymptote, and that usually is at 0. This is going to be your vertical shift, which we know, and I already wrote it on there, is our k value. So in our sines and cosine graphs, we looked for that midline, we shifted up or down. This is the same thing. The k is kind of like the midline. So if I had a +2 or a -3, that would tell me what my horizontal asymptote is, okay? When you do your domain, you're gonna see, if you look at your graph on your calculator, this graph looks like it stops right here, but it does not. It will continue forever and ever and ever, but the calculator stops drawing it because if I have an asymptote right here, remember I can't touch the asymptote, no touch the asymptote. So the graph is going to get so close to the asymptote that the calculator can't draw it anymore because the pixels are too close together. But if you have a good understanding of an exponential and a log graph, you know that it will keep going, okay? So the domain is going to be from negative infinity to positive infinity. I could take this graph and I could pull it out. See if I do this in the right spot. We could create a string that's like a straight line, and it would lay down right along that x-axis. So that domain is going to go from left to right, negative infinity to positive infinity. Sometimes we see this symbol for that, which just means all real numbers, okay? The range is going to go from that asymptote. So my asymptote's right here at 0. And then I could cover up this whole bottom of the graph. My asymptote is all above that graph, okay? So I cover this and I say, okay, everything is above this. So y is above 0 in this case, right? Now I want you to notice that 0 is the asymptote and I don't touch. Remember, no touchy on the asymptote. So that means I do not draw a line underneath. I do not do a bracket. The range has to be a parenthesis. That says parentheses if you can't tell, pretty small. Okay, the intercept is 0, 1 on the parent function, and then the end behavior. This is going to tell me what the graph is doing on the right and the left. So on the right side of the graph over here, the right leg, okay, is going up. So the right is up, okay? And then the left is 0. Now, we don't always put a 0 here. We're always going to match this number with this number. So this is the same thing as k. Okay, so it's going to go on the left side. As I go towards infinity, my graph is going to approach this horizontal asymptote, which we call k. Okay, this is a exponential graph. Now the inverse of an exponential graph is a log. Another thing that you might see is an lnx, okay? Means the same thing, natural log or log. Now a log graph is kind of like an upside down L, which makes sense because it says log, right? And then if you notice where I write the word log, this looks like a straight line, the L. So our asymptote is going to be vertical. It's going to go straight up and down, just like the log does. Okay, just like the log does, it's going to go through 1, 0. So instead of the exponential that's 0, 1, the log graph goes through 1, 0. It's going to follow this asymptote cross 1, 0, our point of origin, and then it's going to go this way. Okay, so the domain and the range, remember these are inverses of each other, and when we do an inverse, we switch x and y. So when I do the domain and range, I'm switching the x and the y. So instead of the domain being negative infinity to positive infinity, the range is, okay? And then the domain is going to be that 0 to infinity. I could cover this side of the graph. My whole graph is on the right side of 0, so 0 to infinity, okay? And another way to write it is x is greater than 0. Okay, and then our end behavior is going to be on the left side, which I don't really have a left side, right? So I have this vertical asymptote, which is a 0. So x approaches 0, and it's on the right side. So I'm going to put a little plus sign right there. And then the graph, I'm either going to say the graph is going down or the graph is going up. So if I'm really close to that 0, I notice that this is going down, okay? So negative infinity is our end behavior. So that's how we're going to do all of these problems as we analyze them, okay? So the next question says, let's graph f of x equals 2 to the x. Okay, so I'm going to, first of all, notice that if I add something to this, it would be 0. So k equals 0, okay? So when I do my domain, it's an exponential graph. It's going to go through 0, 1, and k is 0. So let's just write the horizontal asymptote, y equals 0. So I have to write the asymptote as an equation. So this is going to be y equals 0, and I'm going to draw that dotted line. This is going to go through 0, 1, okay? And then the graph is going to go next to the axis, hit the 0, 1, and then it's going to start growing. So the domain is going to be negative infinity to positive infinity. The range is from the asymptote, so k to infinity. And then if I describe the end behavior here, I would say the limit as x approaches positive infinity, so this means the right leg, and the right leg is going up. And then the limit as x approaches negative infinity, this is the left leg. The left leg is approaching that asymptote, which is 0. So notice that on this one it was a b, okay? And on this one it's a 2. But it doesn't matter because if I put a 0 in for x, whether that's a b or that's a 2 or that's a 550, it's going to be a 1, and it's going to cross through 1. Okay, so that's all we have to do on that. Another thing that you could do to be more specific is create a chart of x and y. So I already know if x is 0, y is 1. What if x is 1? So then I'm going to have 2 to the 1 power, which is just 2 to the 1, which is 2. And if x is 2, it would be 2 to the 2 power, which is 4. So I could go over here and I could get a little more specific on my graph and graph this one, and then 2, 1, 2, 3, 4. So see how that shows you just a little bit better where that graph is going to be. So you're going to want to create a chart. Now you could, just so you can see it, if I put a -2 in here, then I would have 2 to the -2 power. And hopefully you remember, if you have a negative power, it turns into a 1/. So this would be 1/4, which makes sense where it's right here, super low. Okay. So when you graph these, you do need to have 3 points on the graph. Okay. All right, so now we're going to switch and do the log base 2 of x. Well, you're going to love this because remember, this is the inverse of 2 to the x. So if I already wrote my ordered pair, x and y, I'm just going to switch my ordered pair. So my original one, if I look right here, is 0, 1. So I'm going to do the inverse of that, which would be 1, 0. Okay, so it's going to go through 1, 0, and then it was 1, 2, or it was 1, 2, so it would be 2, 1. Okay, and then it was 2, 4, so it will be 4, 2. So all I've done is switched those points, and then when it was -2, it was 1/4. Okay, so this will give us a good idea of the graph, but I could still write down the domain, the range, the vertical asymptote because it's a log, okay, the intercept, and the end behavior. So we're going to write these things down about this graph every time. Remember, end behavior on a log is going to be the limit as x approaches that asymptote. This again is going to be 0 because there's nothing added to this function. And it's from the right side. And then we're going to have our end behavior as it approaches positive infinity. Okay, so the graph is going to cross at 1. There's an asymptote here at 0. And then it will be 2, 1, 4, 2, and then 1/4, and -2 is down here. So that just gives us kind of an idea that it's going to be that upside down L. Okay, so looking at this graph from the left to the right, since there's an asymptote here at 0, it's going to go everything to the right of 0. So our domain is going to be 0 to infinity. The range is going to be -infinity to positive infinity. And the intercept is going to be 1, 0. Okay, as it approaches 0 from the right, so as I go closer and closer and closer and closer and closer to 0, my pencil is moving to -infinity, and then it's going up on this side. Okay, so that was actually showing you 2 functions that were exactly inverses of each other, because this has a base of 2, and then this has a base of 2. So these functions will match exactly to be inverses of each other. If this one was a 2 and this one was a 3, this wouldn't work to do this. So it will only work if they're exactly the inverse, okay? This is going to be the same thing for an e to the x. The inverse of e to the x is the log of x, or the natural log of x, okay? So we're going to get more into detail how we get this and why they are called this. But for this section, you just need to know e to the x and natural log x are the inverses of each other. And if you look at this, it follows the exact same thing, the exact same rules as our normal exponential and log. Okay, so this is exponential, and this is a log, but it's a log that's called a natural log. Okay, so in example 3, we're going to graph this f of x equals -e to the x plus 4. And it actually continues to the other page. So right here, I'm going to write the function. Make sure we get it right. So negative e to the x plus 4. Well, right away, you know what k is, right? So what is this plus 4 going to do, or what is this k value going to be of when we're trying to find this? This is going to shift up 4, right, because of the k. All right, and then the negative in front of that e to the x, that's going to be a reflection. And we have to make sure to say which axis we're reflecting across. So if this negative is in front of the equation, then it's x-axis. But if the negative was just on the x, then it would be a y-axis reflection. Okay, so my parent function for e to the x goes like this and goes up, right? So if I reflect this across the x-axis, instead of going like this and going up, it's going to come like this and go down. So that kind of gives you an idea of what that graph is going to look like, okay? The asymptote, remember, is going to be that k value. So the vertical asymptote, because, oh, no, just kidding, horizontal asymptote, because it is a exponential, let me write that a little bit better, is going to be a y value, and it equals that k value. So y equals 4. And when this says the point on the graph, we're going to use transformations. Okay, so we're going to use transformations. So if my graph, my exponential graph normally went through 1, okay, but I'm moving up 4, so I'm going 1, 2, 3, 4. Okay, we're gonna have it up here. So this graph is going to cross at that point right there, the 0, 5. Okay. Now we have to think about. Remember what we're going to do is we have to reflect it though. So let's actually do this all together. So if I take this point, let's do the reflection first. So if I'm here and I reflect down to here, because it's an x-axis reflection. So instead of being at +1, I shift down to -1. And then from that point, we go up 1, 2, 3, 4. Okay, so make sure we do those in order so you guys can see those. Okay, so this point is going to be 0 and 3. So the point on the graph is going to be 0 and 3 because it used to be 0, 1. I went across the x-axis to -1, and then we added the 4 to get 0, 3. That's using the transformations. The asymptote is still going to be 4. Okay, so it's still going to be 4. So then I'm going to go, it used to go like this. So it stayed close to the asymptote and then it went up. So this is going to stay close to the asymptote and then it's going to go down. Okay, because it reflected across the x-axis. And if it helps, you can look at one reflection at a time, or one transformation at a time. So if this is my normal graph and I reflect it, it looks like this. Okay, and then if I take that normal graph and I move up 4, then I move up 4 from there, that's how you get this. It's 4 units up from the transformation. Okay, all right. So our transformations were up 4, reflection across the x-axis. The horizontal asymptote is the same as our k, our vertical shift, so y equals 4. And then using transformations, we got the point on the graph as 0, 3, our point of origin. Okay. Okay, this is a log graph, and it has an x plus 7 in parentheses, so that means it's going to go left 7, Remember, inside the parentheses, we always do the opposite sign. And then this is going to be down 3. Okay, the asymptote is vertical. It's straight up and down because of I can see that L that looks like a straight up and down line. The vertical asymptote is going to be the K value. In this case is -3. So I'm going to go down here to -3. Okay. Now the point on the graph using transformation. So on a log graph, it typically goes through the x-axis at 1. So I'm going to take that point 1 and I'm going to move left 7. So 1, 2, 3, 4, 5, 6, 7. And then I'm going to go down 3. 1, 2, 3. Okay. So we're going to take this normal point and we're going to go left 7 and down 3. Okay. So what you're going to notice is I keep messing up these asymptotes. Oh, I'm still on spring break, you guys. Okay, I'm so sorry, but I drew the asymptote in the wrong direction. You're probably noticing that wouldn't work to have that asymptote right there. So if I go left 7 and down 3, this is where our starting point is. Okay. So when we do this, we're doing our log is x equals, and it's a straight vertical line. And so our vertical line here is -3, like this. Okay. And then we're moving our graph 7 and 3, and then we can graph it from there. So remember that this graph is I'm still doing the -3. So our domain on a log is going to be greater than -7 because the x plus 7 means I'm shifting the graph left 7. Okay. So 1, 2, 3, 4, 5, 6, 7. I was still doing my horizontal asymptote. Okay, so what I'm going to do is start this one over. Okay, so we're going to start over and get our asymptotes right. Okay, so this is a log graph. This L has a straight up and down line. So our vertical asymptote, when we do our asymptote for a log, we are looking at our horizontal shift, because if you look at a graph and you have an asymptote like this, if you move the graph over to the right or over to the left one way or the other, this line is going to move based off of this part of the function. Okay, so x plus 7, I'm going left 7. So I'm going to take that asymptote that used to be at 0, and I'm going to move it 7. 1, 2, 3, 4, 5, 6, 7. So our asymptote is going to be x equals -7. The vertical asymptote, okay? The graph goes left 7 and down 3. So our normal graph for a log goes through this point right here, 1, 0. So I'm going to move that 7. 1, 2, 3, 4, 5, 6, 7. And then I'm going to go down 3. So this is our point of origin, or our starting point. Okay, and then remember, with a log graph, it looks like an upside down L. So this is going to be our leg that comes down. And then this is going to come, and it goes slow. And it will cross eventually, but it's going to take a minute to cross. Okay, so if I'm drawing it like this is actually going to be underneath there. Okay, and you cannot enter this in the calculator. This too is not able to be entered in the calculator until we go over how to do it. Okay, so left 7, down 3, the vertical asymptote is -7. Now that we have a good graph, let's talk about the domain and the range. So the domain is going to be from this line, which is -7, and then it's going to go forward from there. So I'm going to go -7 to infinity. Another way to write that is x is greater than -7. It has to be a parenthesis. If you put a bracket here, you will miss it. Okay, it has to be a parenthesis. Okay, and then the range goes from the bottom of the graph, and then it will go up forever, even though on my graph, I can't see that. The range on a log will always be all real numbers. It doesn't matter what you do to it. This is your answer for range. Okay. So domain range, we did our vertical asymptote, we did our transformations, we did our point of origin, -6 and -3 would be the point on the graph. Okay. And the last thing we need to do is end behavior. Okay, so this is going to be when I have the limit as x approaches the asymptote, -7 from the right side. I still haven't flipped this over. Okay, I still haven't flipped it over to see what the other side looks like. So we're still doing -7 on the right is going down. And then on the right side of the graph is going up. Okay, so our end behavior didn't change. Even though we moved left and down, our end behavior is going to stay the same. It's negative on the asymptote and positive. Now that's going to change. That will change if we had a negative on here somewhere. And we, instead of going this direction, we went this direction. Okay, then that's going to change that. All right, we have one other little tiny thing at the bottom down here where we're talking about the domain. Now, we've already kind of talked about it up here, but we did our transformation. So right here, a log has to be positive. Okay, so this is where I determine if the log is positive or not. So x plus 1 has to be greater than 0. This is going to move left 1. So my domain is going to be -1 to infinity. Or x plus 1 is greater than 0, and then I subtract the 1 and get -1. We have a couple of examples where we do this, where it has a little bit of algebra involved. So I just want to look at this right here, and I want to set that 4x plus 1 has to be greater than 0. Okay, so if I solve that, I get 4x is greater than -1, and then x is greater than -1/4. So x is greater than -1/4 is going to be the domain. Over here, same thing, 5 minus 3x has to be larger than 0. So you're always just going to circle this part. Whatever's in the parentheses, put a greater than 0 on it, and then solve for x. On this one, I would add the 3x over, and I would get 5 is greater than 3x. And then x is less than 5/3. Okay, I did it this way. I didn't have to change my signs around at all. I just moved the 3x over. If you want to, you can subtract 5 and then divide by a negative. When you divide by a negative, you have to change the direction of the inequality. So instead of x is greater than, x is going to be less than, and that would be the domain. Okay, so that's all for logs. We will go over it in class. Let me know if you have any questions. Have a great day.